Hello and welcome back. Last time we discussed in the previous video the ways that we could change velocity, and we realized there's two ways we can change velocity. We can change the direction part of the velocity, and that's going to yield one type of acceleration called tangential or linear acceleration. In this text we use subscript t for that type of acceleration, a sub t. And the second way we can change velocity is by changing the direction part of the velocity, and that will yield an acceleration that is known as radial or centripetal. This particular text will use the subscript c for centripetal. So two different types of acceleration that we want to keep track of. And as we start talking about motion that has to do with changing direction or moving through circles, then there are some other quantities that are going to be easier for us to define and be able to use rather than the quantities we've been using for just linear motion. So what I've done here is draw a circle with an object that is moving through circular motion, and you can see the sense of the direction I have for the arrow right here for the motion of this wheel. You can think of it as, for example, the old vinyl that when I was a kid we listened to our favorite music on, and so we would get these records or vinyl and we would put them on a turntable and then turn on the turntable, and it would start increasing the rotational speed of the record until it hit the speed at which it was manufactured for us to listen at. And for a small piece of vinyl, it would be 45 revolutions per minute would be that speed at which we would want to hear the record being played at. So notice that I just picked a couple of points here to show the ease with which we can describe those points using a different type of coordinate system than we've been using. So I've superimposed the XY coordinate system, or the Cartesian coordinate system, on this motion, and you can see I've also defined the radius of the circle that this point is moving through. So point 1, P1 right here, this point at this location, P1, can in our Cartesian coordinate system be defined as some x1, y1. So that's just how far out on x I have to go and how far up on y I need to go to be at position P1. Likewise for position P2, I can also define it in the Cartesian coordinate system as how far I need to go x2 along the x-axis, and then how far I need to go y2 up the y-axis. So I can define those points in terms of x's and y's as we've been doing up until now. But when we're dealing with an object that is moving through circular motion, it becomes more convenient to introduce a different coordinate system to use. And it's one that I'm sure you were introduced to in your mathematical studies in high school, and that's called the polar coordinate system. So remember, the polar coordinate system only deals with two dimensions, which is what we are dealing with, right? Just x and y. In the polar coordinate system, that's going to be some r and theta. And so if I want to describe position P1 in terms of our polar coordinate system, then I would just describe it's the magnitude and direction form of the vector. How far away I am from the axis of rotation, r, and the angle that it makes with respect to the x-axis, theta 1. So r and theta 1 would be the polar representation of the Cartesian x1, y1. So notice that this is the same thing we've been doing as far as going from component form to mad form. The polar form is the mad form, and the Cartesian form is the component form. So this is the same thing we've been doing. Position P2, likewise, I can define it in polar coordinates as some distance r from the axis of rotation and some angle theta 2 from the x-axis. And so defining position P2 is r theta 2. So Cartesian representation of the points and polar representation of the points. Now, as my object, and again coming back to the vinyl, some dust particle, let's say, that is actually on my piece of vinyl is rotating, and let's say that my record at this point has reached a uniform speed, and so it's just rotating at 45 revolutions per minute. I can talk about the angle through which my dust particle moves as it moves from position 1 to position 2. And so the change in angle is defined then as theta 2, the final angle, minus the initial angle, theta 1. So that's the change in the angle. We need to define another quantity that talks about how quickly that point moves through that angle, and that's called angular velocity. Now be careful here. This is not the same thing as our velocity. This is angular velocity and has different units associated with it. Gets the symbol omega, which is a letter from the Greek alphabet, looks like a pregnant W, and it's equal to the change in angle divided by the change in time. The units standard that we will have for omega are going to be radians per second. So radians is the standard unit for angle, and seconds, of course, standard unit for time. All points on the rigid wheel are going to have the same omega. So all points on this wheel are going to be tracing out the same number of revolutions, rotations, radians, degrees per unit time, no matter what units we use, whether we're in standard units or any other units. All points on a rigid wheel, and be careful here, we are saying on a rigid wheel, in other words, all points are cemented in place. They're all going to move through the same number of rotations, radians, degrees per unit time. So there's a difference, though, in their linear speed, and that is how fast they have to move in one full rotation to get through that full rotation. And so obviously not all points on the wheel are going to have the same linear speed. It's going to be dependent on how far away that point is from the axis of rotation. Notice that if I'm standing on the axis of rotation, I don't have any linear speed at all. I just simply am rotating in about an axis right through the center of my head. But as I start moving away from the axis of rotation, the circle I have to trace out for a revolution is becoming larger and larger and larger. And points closer in are tracing out smaller circles in the exact same time. So that means that the further away you are from the axis of rotation, the larger linear speed you must have. And so linear speed then is properly defined as the angular velocity, which all points on the wheel have the same angular velocity, times how far they are from the axis of rotation, r. So the linear speed scales as r. When r is 0 and you're right here at the center, you have no linear speed. But as you start increasing r, moving further and further from the axis of rotation, then your linear speed starts increasing. Notice linear speed is going to have the same units that we've been using for linear speed all along, and that's standard units of meters per second. So standard units for v are going to be meters per second, as they have been always. But notice that technically we have radians per second times meters. Radians is a special unit that kind of morphs in and out whenever it's convenient. Notice that we never define the linear speed as radian meters per second. We drop the radians and just express it as meters per second. So here it's super important that omega must be in radians per second for this formula to work, okay? So for this formula right here to work, omega must be in radians per second, okay? And when it is, then the linear speed that you get will just be in the standard units of whatever distance you have r in. Standard unit is going to be meter. You're going to drop the radians and just have per second or per minute or per hour or whatever time units. But the angle units must be in radians. All right. What about when I first turn on my vinyl? Okay, so here I am, I'm anxious to listen to my album, and so I put it on the turntable, and then I apply power to the turntable. What happens? Well, initially it's not rotating at the speed at which I want to listen to this vinyl. So we're rotating starting from 0 up to that cruising speed that I want to listen to the record at. During that time, the angular velocity is changing. At first it has 0 radians per second, but as I as I increase in the speed, now it's maybe 1 revolution per minute, and then 2 revolutions per minute, and 3 revolutions per minute, et cetera, until it gets up to the 45 revolutions per minute that I want to listen to the record at. During that time, as it's changing angular velocity, then we are experiencing an angular acceleration. Angular acceleration gets the symbol alpha. Another letter from the Greek alphabet looks like a fish. And it's equal to the change in angular velocity divided by the time over which that angular velocity changed. Notice that the units we're going to have for angular velocity are going to be equal to radians per second squared. So remember that we have radians per second as the standard unit for omega, and then seconds for time, so that's going to give us radians per second squared. Now, both angular velocity and angular acceleration have direction associated with them, but at this level of physics studies that we're going to be looking at for your introductory year of physics, we don't worry about the direction parts of the angular velocity and the angular acceleration. So these are the definitions we're worried about right now, and in the next video we will connect some of these quantities to some of the quantities we've seen before and start applying them to problems so that we can actually see them in action. We'll see you next time.